A 2-kilogram block slides down a frictionless plane, inclined at 30 degrees above the horizontal. What is the acceleration of the Z-block?
Draw a picture! Alright, first up, draw a picture. We have a block on an inclined plane. There's not much more we can draw, except let's talk about our axes, which way is positive, where horizontal stuff is, and where vertical stuff is. Alright, so normally you're used to seeing your x and y axis like this, right? This is your y axis, and this is your x axis. Y is usually up and X is usually side to side, right? If we use this in our problem, it would make it much more complicated. What if I turned my X and Y axis like this? It's still the same set of axes, I just twisted it. For this problem, I want to tilt my X and Y axis. I want my X axis to be parallel to the plane. That way when we're talking about X stuff or horizontal stuff or side to side stuff, we're talking about going along the ramp, parallel to the ramp, and that'll make this problem much easier. So instead of my traditional x-axis, I'm going to draw my x-axis parallel to the plane. Okay, and my y-axis therefore is always perpendicular to the x-axis, so it would be this way. Okay, so this is my new coordinate system. If you don't like this, tilt your head to the right, and now it looks like my y-axis is pointing up as it usually does, right? Or you can tilt your paper, whoop, and there my y-axis is up. So really all we're doing is tilting our coordinate system. That doesn't change anything about the problem. Whenever you're dealing with an inclined plane problem, you want to make your x-axis, or your side-to-side stuff, parallel to the incline. 2. Label your nose. Your knowns. Label your knowns. We know the mass of this box. The box has a mass of 2 kilograms. We know the angle of the plane. That angle, I'm going to call it theta, and we know it's equal to 30 degrees. And the reason I'm labeling the 30 degrees at this angle and not at the top angle is because the problem said 30 degrees above the horizontal. Alright, that's what we know from the problem. But if we're dealing with an inclined plane, we've got some forces going on. Whenever you have this kind of a problem, I can't force you to do it, but I highly recommend drawing a free body diagram. So, as far as we know, this block is on Earth, so there's obviously a force of gravity, and the force of gravity always points downwards. Even though we tilted our coordinate system, right? The Earth is still down here, right? This is the Earth. So gravity still points downwards to the Earth. We can change our coordinate system, but we cannot change which way gravity is acting. We are going to give this arrow a name and call it F sub g for force of gravity. Now, this block is on a plane, and so it's partially pushing on the plane, which means that the plane is going to push back, and there's going to be a normal force. And if you remember, the normal force is always perpendicular to the surface.
You're normally used to drawing the normal force upwards,
or in the opposite direction to the force of gravity. However, our surface here is tilted, right? So we need to take that into account when drawing our normal force and make sure that our normal force is still perpendicular to the surface.
Remember, the normal force isn't always acting in the opposite direction to the force of gravity.
My incline is this way, so perpendicular to that would be this way. And I'm going to give this arrow a name, F sub n. There is no friction in this problem, so this looks like the only two forces acting on the box. Before we're done, let's talk about the force of gravity. What we've drawn here is correct. However, to make our calculations, we're going to need to do something to the force of gravity. We want to split the force of gravity into its x component and its y component. And so you're thinking, what do you mean? It's acting downwards along our y-axis. What are you talking about? Oh, well, remember, we switched our coordinate system so that our y-axis now is actually perpendicular to the plane. What we want to do is split gravity into its component along the y-axis, or perpendicular to the plane, and its component parallel to the plane, or the x component of gravity. We're going to draw the well-known triangle that you are always going to draw when you have an inclined plane problem and need to split gravity into its components. The y component of gravity is going to be perpendicular to the plane. because our y-axis is oriented perpendicular to the plane.
Dun dun dun.
Our x component of gravity must be parallel to the plane.
Dun 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 dun.
I'm going to call this purple arrow FGX and this red arrow FGY. This stands for the vertical component of gravity and the horizontal component of gravity. Did we just add 2 more forces to the box? No. The red and the purple arrow together are another way of looking at the force of gravity that we drew in the first place. So this blue arrow by itself is the same thing as this red arrow and the purple arrow together. We're looking at the same thing in 2 different ways. So if I cover up that blue force of gravity arrow, the red and the purple arrow have the same effect as the arrow that we just covered up. By looking at the force of gravity in terms of its y and x components, now we can talk about the forces acting along our x-axis and the forces act along our y-axis. When we had the force of gravity pointed downwards, it didn't match our axes at all. So when you make this triangle, the other thing to note is that the angle right here between the red arrow and the blue arrow is the same as the angle of the inclined plane. So this theta here, the 30-degree angle, is always going to be the same as the upper angle of your triangle here. So I'm going to call this theta. Now, if we know the mass, we can find the force of gravity. That should be something automatic that you do. So recall that the force of gravity is equal to mass times the acceleration due to gravity. If we say g is 10, then the force of gravity is just 10 times the mass. So we can say that the force of gravity is equal to 20 newtons. Alright, so this is everything that we know. What is our target? Part A asks us to find the acceleration of the block. Our target is A equals question. The block is moving down parallel to the plane in this direction. This direction is our positive x-axis. So really, we're looking for our acceleration in the x direction. Alright, my next step is to find an equation. Remember, our equation has to have our target variable in it, so we need our equation to have an acceleration. I have a bunch of forces, and I know the mass. So I need an equation that has some forces, a mass, and an acceleration. And hopefully you're thinking of the number 1 forces equation that you should always go to, and that is Newton's second law. Net force equals the mass times the acceleration. So if we want to use Newton's second law, and we're looking for the acceleration in the x direction, we need to talk about the forces acting in the x direction. So when we say net force, remember we are adding together all the forces. Because we're talking about the x direction, this is the net force in the x direction. My next step is to plug in my zeros. I don't have any zeros, so I have nothing to plug in. I am going to rewrite my net force, though, into the component forces. If I come back and look at my picture, I want to find all the forces acting in the x direction. Because our x-axis is parallel to the plane, I'm looking for the forces acting parallel to the plane. My normal force is acting perpendicular to the plane. That's not one of them. Here's where you're going to see why we broke the force of gravity into its components. The vertical component of gravity is perpendicular to the plane.
So this component is having no effect on the motion parallel to the plane.
However, the x component of gravity, it's acting parallel to the plane, which means it is causing an acceleration parallel to the plane. And so it is this horizontal component of gravity that is accelerating the block down the plane. Because we have no friction, the horizontal component of gravity, Fgx, is our only force acting in the horizontal x direction. So our net force in the x direction is Fgx, that is equal to ma. My next step is to isolate the variable. So I'm going to divide by m, meaning the acceleration is Fgx over m. Oh, and this is our a sub x, our horizontal acceleration. So we know the mass, horizontal component of the force of gravity. Can we find it? We most certainly can. We know the entire force of gravity, 20 newtons. We know this angle theta, so which means if we use some triangle math, or trig, we can find this side of the triangle, or the horizontal component of gravity. Because we want the side opposite to the angle, we're going to be talking about sine. So this side of the triangle is going to be the total force of gravity times the sine of this angle. So the horizontal component of gravity can be replaced FG sine theta. Now I can plug in my numbers. So my acceleration in the x direction is equal to the force of gravity. Come back here, it is 20 newtons. So 20 times the sine of theta, our angle is 30 degrees. Remember, this angle theta is the same as this angle. And divide by the mass, which is 2 kilograms. So our acceleration is 5 meters per second squared. Remember, we're talking about acceleration, so our units are meters per second squared. What this means is that the block is accelerating in this direction at 5 meters per second squared.
Which makes sense, because that is our positive x-axis.
What if I didn't give you the mass? What if you didn't know what the mass was, and you didn't know what the force of gravity was? Could I still solve this problem? The answer is yes. If I go back to this step right here, I can replace the force of gravity with mg. Remember, we said force of gravity is equal to mass times the acceleration due to gravity. So I could rewrite this as mg sine theta over m. And what happens? The masses cancel out. And so you actually don't even need the mass to solve this problem. In a problem, if you're not given the mass, that's okay. It's probably going to cancel out.